Radiation heat transfer. Theory and properties. All right, so if you're a first-year chemical engineering student, this is for you. This stuff is absolutely fundamental because it's all about how energy moves through electromagnetic waves. It's critical for designing everything from furnaces to heat exchangers. First up, the physical mechanism. So, thermal radiation is just electromagnetic energy that an object gives off only because of its temperature. And this energy, it travels at the speed of light. The key thing to remember is that the energy travels in these little discrete packets called quanta. Basically, it just means higher frequency waves carry more energy. Second, you've got to understand the black body. Think of it as the perfect radiator and absorber. It just soaks up all the radiation that hits it. Its power is described by the Stefan-Boltzmann law, which basically says that the hotter it gets, the way more energy it radiates. We're talking temperature to the fourth power. And here's a great shortcut, Kirchhoff's identity. It just means a surface's ability to emit energy is the same as its ability to absorb it. Finally, what about real surfaces? The black body is just an ideal, right? Well, when radiation hits a real surface, it can do one of three things. It can reflect, get absorbed, or pass right through. To make analysis simpler, we often use a model called a gray body, where we just assume its ability to emit energy is the same no matter the wavelength. So, getting a handle on these key ideas and laws really gives you the foundation you need to solve pretty much any radiation heat transfer problem. Let's dive into more detail.
In your heat transfer classes, you've probably covered conduction and convection, right? But there's this third, really fundamental way that heat moves around, and it's behind everything from the cozy warmth of a campfire to the sheer power of the sun. Yep, we're talking about thermal radiation, and today we're going to demystify it completely.
Really think about it for a second. Conduction needs stuff to touch. Convection needs a fluid, like air or water, to move the heat. But the huge void of space, it has neither of those. So how on earth does all that energy from the sun get here? Well, the answer is thermal radiation. It's this incredible form of energy that needs no medium at all. It just zips right through the vacuum of space. To get a real grip on how this works, we're going to treat it like we're cracking a series of codes. First, we'll cover the basics. Then, we'll unlock the secrets of perfect radiators, move on to how real surfaces work, talk about the color of heat, and finally put it all together with the geometry factor. Ready? Let's go.
Okay, let's start with the absolute fundamentals. At its very core, thermal radiation is just one flavor of something you already know about, electromagnetic radiation.
Just like radio waves or the visible light coming from your screen, thermal radiation travels as electromagnetic waves, or you can think of them as tiny packets of energy called photons, and they all move at the speed of light. The big difference here is that thermal radiation is given off by any object just because it has a temperature. Seriously, anything that's above absolute zero is radiating energy right now.
All right, time to crack our first code. You know how in engineering we love to start with a perfect, ideal model to make sense of things? Well, for radiation, our ideal model is something called a black body.
The really cool thing about a black body is its two-sided personality. On one hand, it's the perfect absorber. Any radiation that hits it gets completely soaked up. None is reflected. But on the other hand, it's also the perfect emitter. For any given temperature, nothing can possibly radiate more energy than a black body. It basically sets the ultimate speed limit for radiation.
And this brings us to our first major breakthrough, the Stefan-Boltzmann law. This super elegant equation is the key. It tells us exactly how much energy a perfect black body pumps out. Let's break this formula down piece by piece. First up, we have E sub B. That's the black body emissive power. Just think of this as the intensity of the radiation. It's the amount of energy, in watts, pouring out of every single square meter of the surface. This is the number we're trying to find. Next is that Greek letter sigma. That's the Stefan-Boltzmann constant. Now, don't let the name intimidate you. It's just a constant of nature, a fixed number that makes sure all the physics and all the units work out perfectly. It's the magic number that connects temperature to emissive power.
And finally, we have T for temperature. Now, this is absolutely the most important part, so listen close. T has to be the absolute temperature. That means you must use Kelvin, not Celsius, not Fahrenheit. Kelvin. And look at that, it's raised to the fourth power. This is huge. It means that if you double the absolute temperature of an object, say from 300 Kelvin to 600 Kelvin, you don't just double the radiation, no way. Because it's to the fourth power, you increase it by a factor of 16. That is an incredibly powerful relationship. Okay, that was code 1. Black bodies are a fantastic starting point, but let's be real. Nothing in our world is a perfect black body. So we need a way to handle actual, real-world objects. So when radiation hits a real surface, only 3 things can happen. It can bounce off, which is reflection, it can get soaked up, which is absorption, or it can pass right through, which is transmission. And because energy can't just disappear, those 3 fractions have to add up to 1. Now, for most of the solid things we deal with every day, like a chunk of metal or a concrete wall, nothing gets transmitted. And that simplifies things for us, right? It means whatever isn't reflected must be absorbed. So how do we tweak our Stefan-Boltzmann law for the real world? Easy. We just add a little correction factor called emissivity, which we write with the Greek letter epsilon. It's just a simple ratio, a number between 0 and 1. It tells you how good your real surface is at radiating compared to that perfect black body at the same temperature. A shiny, polished mirror, its emissivity is going to be close to 0. A piece of black soot, that's almost a perfect. And this leads us to this really elegant and powerful rule called Kirchhoff's identity. All it says is that for an object that's in thermal equilibrium, its ability to absorb radiation is exactly the same as its ability to emit it. So a good absorber is a good emitter. A bad absorber, like something really reflective, is also a bad emitter. This little identity is a massive shortcut and a ton of engineering problems. Okay, let's have some fun with this. Time for a little quiz. Based on what we just learned about good absorbers and emitters, which one of these do you think is blacker when it comes to thermal radiation? A lump of coal or a pile of bright white snow? And the answer is the snow. I know, right? It's totally counterintuitive. But this is such a perfect example of why you can't always trust your eyes with this stuff. An object's color in the visible light we see can be completely different from how it behaves with thermal radiation. To long-wavelength heat, that bright white snow is actually a nearly perfect black body, soaking up and spitting out radiation super efficiently. This actually leads us perfectly into our third code, the color of heat. So far, we've only talked about how much energy gets radiated, but now we're going to talk about the kind of energy. This whole idea is governed by something called Wien's displacement law, and what it tells us is there's this really cool inverse relationship. As an object gets hotter, the peak wavelength of the energy it's emitting actually gets shorter. And you've seen this. Think about a blacksmith heating a piece of iron. It starts glowing a dull red, then gets brighter red, then orange, and finally it's glowing white hot. That's Wien's law in action. The peak wavelength is shifting right down into our visible spectrum.
Okay, we have almost cracked this whole thing. There was just one last final code to unlock. See, it's not enough to know how much energy a surface is emitting. We also have to know how much of that energy actually makes it to another surface, and that is all about geometry.
And for that, we use something called the radiation shape factor, or sometimes a view factor. It's just a number, between 0 and 1, and all it tells you is what fraction of the energy leaving one surface hits another surface directly. Think about it. If you're standing in a tiny closet, the view factor from you to the ceiling is pretty big, right? But if you're standing in the middle of a huge field, the view factor from you to one little cloud in the sky is going to be incredibly small.
Now, figuring out these shape factors can get really hairy, but luckily for us engineers, we have an awesome trick up our sleeve called the reciprocity relation. It says that the area of the first surface times its view factor to the second one is equal to the area of the second surface times its view factor back to the first. This beautiful, simple relationship saves us from doing tons of complicated math, and it's essential for solving real-world heat exchange problems.
So, there you have it. We've cracked all the codes. We have the Stefan-Boltzmann law for the amount of heat. We have emissivity to handle real surfaces. We have Wien's law for the type of radiation. And we have the shape factor to account for the geometry. So the final question is really for you. How would you use these codes? If you were designing a solar panel, you'd want a surface with high absorptivity, right? And you'd want to maximize its shape factor to the sun. But for a spacecraft's heat shield re-entering the atmosphere, you want the exact opposite. You want very low absorptivity to avoid soaking up heat and very high emissivity to radiate all that energy away into space. The codes are always the same. The true engineering challenge is learning how to apply them.